Hello everyone. So let's continue our discussion and then of electromagnetic induction. And in this video, I'm going to talk about Lenz law. So if you recall, in our previous video, we were talking about EMF induced is equal to n d phi by dt, rate of change of flux linkages. This is proposed by Faraday in the year 1831. What Lenz in the year 1835 has suggested is that EMF induced is minus n d phi by dt. So while the magnitude is correct, just a technical matter, that is the direction of the EMF should be minus here. Okay. So what in other words Lenz is saying is that the EMF induced will be in such a direction that it will oppose its own cause of production. Okay, what is the cause of the production? That is rate of change of flux linkages. That is opposed, and then EMF induced in such a way that it opposes it. So, what does it actually mean? Okay, so let's get some meaning into it. Okay. So, if you again recall in my previous videos, I've talked about the experiment. Okay, the experiment is something like this. Okay, so we have a coil. So the coil is placed like this between 2 centimeters to 3 centimeters, and the other side of the coil is between 6 centimeters to 7 centimeters. The in between part of the coil does not matter because we are only considering the experiment where the magnetic field is cutting the left part and the right part of the coil. Okay. So, and the magnet starts from position 0 and moves gradually towards position 10 on the right side. So, as the magnet is moving at a speed of 1 centimeters per second, okay, so magnet is moving at a velocity of 1 centimeter per second, some flux is cut by this coil and the EMF is induced. Okay, so now the question is, what is the direction in which the EMF is induced? Okay, so that is a question we are trying to investigate. Okay. So one of the right now, if we don't worry about the direction, if we worry only about the magnitude, okay. So if I go down, we have seen that the total flux is 80 milliwebers, and when the position 0, the flux linking with the coil is 0, and gradually when the position comes to position number 3, the entire 80 milliwebers is linking with the coil, and therefore the flux linkages will become 80 milliwebers into 200 turns, so that is 16 webers of flux linkages. Sorry. So this flux linkages will induce some EMF. So 16 webers is the change in flux linkages in 1 second. So 16 volts is the EMF induced. Okay, so the magnitude of it. So that's what we did in this calculation. So here 16 volts are induced. Okay. Now imagine, I'll just draw the fresh diagram once again. So imagine that the coil is here. So I just draw it in an isometric view. The coil is like this, or let me just take only one turn. Okay, so just for simplicity. Okay, so this point let's call it A, and this point let's call it B, and then on top of it there is a magnet. So this magnet is south pole and north pole, and then the magnetic flux lines are coming down like this. So right now all the magnetic lines are not linking with the coil. So as the magnet moves like this, so the flux will link with the coil. So my question is, what will be the direction of the EMF induced in this conductor and in this conductor? So let's mark these points. This point as 1, and this point as 2, and this point as 3, and this point as 4. Okay. So among these points 1, 2, 3, 4, what is the direction of EMF induced? Okay. Now, if I compare with the previous example, I know the magnitude, that is 16 volts. Let's say the same numbers apply. So 16 volts. So here, let's say if I connect a resistance of 2 ohms. Okay. So I get 16 volts induced EMF, and then 2 ohms is the resistance. So the current that will be flowing is 8 amperes of current. Okay. I don't know the direction, so that's why is it 1 to 2 or 2 to 1, or we don't know the direction. but at least 8 amperes of current is flowing. So what is the power consumed in this resistance? So power, as you know, is I square R. Okay. So I square R, that is 8 into 8 into 2. Okay. So 8 into 8 is 64. 64 into 2 is 128. Okay. So 128 watts. Okay. So this much power is consumed, and if you remember the previous experiment, the EMF was maintaining at 16 volts for duration of 1 second. Okay, so this 128 watts is the power, and if I multiply it with time of 1 second, so I'll get the 128 joules of energy. Okay, so what I'm saying is, if I connect a load here, electrical load, the electrical load is receiving some energy. Okay, and that energy that it is receiving is 128 joules. Okay. So the question that Lenz asked is, how can we get this free energy from sun? What about law of conservation of energy? If I am getting 128 joules here, where is the 128 joules going into the system? Okay, so the 128 joules is the output. Where is the input of 128 joules? Okay. So the input of 128 joules is what we have to worry now. Okay. So what happens is, so now we are trying to push the magnetic field down into the winding, right? So if this is my winding 1, 2, 3, 4, I am trying to push the flux into the winding in this direction. Okay? So the winding will have to create a current, or have to create an induced EMF, and therefore the current in the opposite direction. Okay. So only then what happens is, we like imagine that there's a giant north pole here. Okay. So which is giving the magnetic field an upward direction, and I'm trying to push the magnetic field downward direction. So two north poles. So imagine if you try to bring two north poles together, there will be a lot of repulsive force. So that repulsive force, you have to do some work. So force into distance. So this is the distance, and force. Force into distance is nothing but work done. Okay. And the logic is, by the time I move from here to here, I have to push the north pole opposing to the another north pole. So force is generated, I have to push it. So in that pushing, some mechanical work is done, and 128 joules of mechanical work is done here. That mechanical work of 128 joules, from maybe from position 0 to position 3 or 4, just to crossing this side, that much of energy is being consumed, or is being converted from mechanical energy. So basically, this is moving. So mechanical energy converted to electrical energy. So 128 joules is input here, and 128 joules is output here. So this is the observation made by Lenz. Okay. So the logic is, the north pole and north pole should be opposing force. Only if there is opposing force, then the work will be done. Imagine if this was south pole. Okay, the south pole would very happily accept the north pole. In fact, the south pole will simply attract the north pole closer to itself. Magnetically, it will attract, and therefore there won't be any work done, and still we'll get the output, which is not the possible thing. So therefore, it has to be the magnetic field generated here has to be such that it is going upwards, as if there's a giant north pole below this coil, and then giant south pole above this coil, and then the magnetic field is coming. So north and north should oppose each other. So what should be the direction of the current, so that the magnetic field is like this? So the magnetic field is, of course, outside the coil it will be downwards, but inside the coil it will be upwards. Okay. So by this, I can easily tell that the current direction should be like this, from 2 to 1. So the voltage will be also in this direction, from 2 to 1. Okay. So from high voltage to low voltage, something like that. So that is what is happening here. Okay. So we know the corkscrew rule. If there's a current carrying conductor, and the current is going downwards like this, then the EMF induced will be anti-clockwise around it. Okay. So you can use the corkscrew rule for that, or the right hand rule, or different rules are there. Okay. So why the current is going from 2 to 1? So that we produce a north pole inside it. Okay. Now let's continue the discussion. So I said, if I go up, there is one sorry, there is one peak of 16 volts here, then there is another minus 16 volts here. Okay. So let's think about that now. Okay. Now imagine that the magnet is already here. Okay, so this is south pole, this is north pole. Already a lot of flux is going down like this. Okay. Now I want the magnet to go out of this conductor number 3 to 4. Okay. So at this time, because already the flux linkages are there here, and then this is going outward, the magnet, I mean the conductor will have to induce EMF in such a direction that it opposes the north pole going out. Okay, so that is possible when a big south pole is generated here. Okay, so this above north pole is actually the magnet which is moving, whereas the below south pole is created so as to attract the north pole towards itself and force it not to move towards the, not to go out of this coil, just to keep it back. Okay. So again, I hope you understand the logic. It takes effort, it takes work, mechanical work, to push the magnet from outside to inside the coil. It also takes the effort to push the magnet from inside to outside the coil. Okay. While it is pushing from inside to outside the coil, south pole is created. So at that time, for south pole to be created, again the magnetic field has to be like this, so it has to be in the opposite direction. Now the current should flow from 4 to 3, then it creates a south pole here. Okay, so overall if you see, the EMF induced will be opposing the very cause of its production. So to signify that, the sign that is taken is EMF induced is minus n d phi by dt. Okay. So to maintain the law of conservation of energy, Lenz has observed, and then he has corrected Faraday. This was done in the year 1835. Okay, that the minus sign is to be there. So of course you can always assume that this is my positive terminal, this is my negative terminal, then it is one direction. If I reverse my assumption that this is positive and this is negative, then I can even argue that E is n d phi by dt. So it also matter of convention which direction you are assuming, but then physically looking at it, in order to maintain the law of conservation of energy, this is the Lenz law. So finally, to summarize the discussion over 3 videos, this is what is the important equation that you should remember. That is, EMF induced is nothing but minus n d phi by dt. So based on this equation, let's work out some numerical example problems. I hope you have understood something from this video. So if you have any doubts, feel free to ask me.